right, I think we're good to go. So, hopefully the heat doesn't get too bad because the air conditioner makes it really loud in here. But we'll see what we can do. All right, work the weekend, yeah, that happens. Let's start with questions on the homework or on the lab that you're working on.
Yeah, actually, because I was so busy this weekend, I do have questions on the lab.
Okay.
I tried looking through the data sheet. Thank you very much, data sheet. And for the life of me, I was finding lots of different stuff online and some hit or miss stuff in the data sheet. But on 58, it asks like,
Oh, is this on the homework?
yeah, this is
Okay.
on 58. Assume the PIC system clock runs at 4 megahertz. Divide by 4 to get frequency of 1 megahertz. How long does one instruction take? I'm kind of curious, like, what is the equivalency here? What is, like, the actual...
All right, so let's write some of this out.
Because I got such varying information.
Yeah, and there's a lot of information out there, and some of it's better than others, and some of it's just not applicable. So here's the world of instruction timing that we're kind of interested in for 270. So suppose the system clock is 4 megahertz. All right, so mega is million. It's 4 million ticks per second. The way that the PIC processor works, if you take the system clock and divide by 4, that gives you the instruction clock. I should be using the word frequency here, but frequency sounds scary. So if the system clock is 4 megahertz, the instruction clock would be 1 megahertz. And the instruction clock is basically how many instructions you get to do per second. There's exceptions to that, but we generally think of the instruction clock as the number of instructions you do per second. So in this first question, if the system clock is at 4 meg, divide by 4 to get an instruction frequency of 1 megahertz. Okay, so 1 million instructions per second. And then it asks, how long does one instruction take? So the main thing with all of these timing issues in computer architecture is knowing, what goes on top, what goes on bottom when you take a reciprocal. So 1 million instructions per second. So you can translate that into how many seconds does it take to do an instruction. And there's kind of cheap ways to do this by just playing with units, and so 1 million instructions per second would be 1 second per million instructions, but that's also 1 millionth second per instruction. So there's different ways to think about this. You do this in physics courses usually, figuring out how to work with units like this. But the punchline in this case is if you can do 1 million instructions per second, it takes 1 millionth of a second to do one instruction. Right? So it's a reciprocal. So 1 millionth of a second, that's just a microsecond. If you had a millisecond, that's 1,000th of a second.
So, I have a quick question.
Mm-hmm.
So, if the instruction clock is a fourth of, like, the system clock, that's basically the time it takes to decode the instruction, right?
It's the time it takes to fetch and decode the instruction.
Okay.
And it actually takes 8 ticks of the system clock to fetch and decode an instruction and execute it. But we have that pipelining thing, so we effectively double the speed of instruction execution.
Okay.
And it's there's a state machine and the clock ticks, and in state 0 it puts the program counter on the address bus, and in state 1 it asserts the read signal, and in state 2 it takes the value coming from the memory and latches it into its internal instruction register, and in state whatever, it does something else, and it goes through a series of steps, and this stuff happens sequentially. So every processor, there's a certain number of ticks of whatever the underlying clock is, which for us is the system clock. Certain number of ticks that need to happen to fetch an instruction from memory, set up the inputs to the arithmetic logic unit, or move things around, and so on and so forth. So
I did some reading on differences in ARM x86.
Ah.
There's an argument over time to decode.
Yeah.
I'm wondering if that was related to this here. So.
Yeah, so I mean, part of this is decode time. And, arguably a RISC processor with only, 30 instructions is easier to decode than something with a few thousand instructions. But it depends how you set the instructions up, too. The binary coding of instructions on the PIC is set up in a way that I think makes it easier to build the hardware that does the decode. Because, the first 6 or 7 or 8 bits are always the opcode, and the last 8 are generally the file register or the literal constant or things like that. So, but yeah, that's all good computer architecture stuff. All right, so does 58 make sense? If it runs at 4 megahertz, instruction frequency is 1 megahertz, one instruction would take 1 microsecond, a millionth of a second. Is everybody good with that?
Yes.
So then, how long do 100 instructions take? That would just be 100 microseconds, right? Because if 1 takes 1 microsecond, 2 would take 2 microseconds, 10 would take 10 microseconds, 100 instructions would be 100 microseconds. And then this is all just kind of playing with the algebra, basically. So how many instructions would execute in a tenth of a second? Well, a tenth of a second is how many microseconds?
$100,000?
Yeah. And one way to do that is, 1/10 of a second. And you can do 1,000,000 microseconds is 1 second. And then you do this thing that teachers don't like, but it usually works. So I did 1/10 of a second, and here I just wrote down 1 in the form of 1,000,000 microseconds is 1 second, and then I'm going to cancel these units. And so I get 1,000,000 divided by 10 microseconds, that's 100,000 microseconds.
Unrelated, why does that bother teachers?
I don't know. I mean, it feels like kind of cheating somehow, but we cheat all the time, right? If we didn't, we'd be, nematodes or something. We make these conceptualizations and we do things, but I think there's probably something in here that's not quite kosher, but I don't know.
I'm curious because I was taught that method in high school in my chemistry class.
Yeah.
Back in the day, that was 15 years ago, something like that. 15
Okay.
years ago.
Okay.
Is that changed?
No, okay. Well, I'll take it as a legitimate thing then. I kind of got the fisheye from my teachers sometimes when I did this, but that was, a long time ago. So, yeah, do this. Embrace it. I like it. All right, cool. So what were we trying to do? How many instructions was executed in a tenth of a second? 100,000 instructions. And then let's see. All right, and then the same thing, but instead of assuming the system clock is 4 megahertz, assume it's only 32 kilohertz, which is the default clock rate. But same thing, if it's 32 kilohertz, what's the instruction frequency? Yeah, so system is 32K. instruction divided by 4, you get 8K. So how long does it take to execute one instruction? (8,000 instructions per second). How long to execute one instruction?
125 nanoseconds, or microseconds.
Alright, I'm going to be lazy and say 1/8,000th of a second. But yeah, if you go ahead and multiply that out, that's 125 microseconds. Perfect. And then, and you can kind of brush aside a lot of the business of units and conversions and metrics if you have a calculator. But it's nice to be able to do something like, convert it to a unit where you have a nice number with a few digits instead of, 0.000125 kind of thing. All right, and then how many instructions execute in 1/10 of a second? So 8,000 per second. How many in 1/10 of a second? Yeah, 8,000 divided by 10. If you ran for a half a second, you'd do 8,000 divided by 2, which is 4,000 instructions. If you ran for an 8,000th of a second, you do 8,000 over 8,000, which is one instruction. Which is what we already figured out. One instruction takes an 8,000th of a second. So those are good exercises to go back to and think about and play around with. And particularly this week when we're working with timers, we're going to be doing a lot of calculations like this. And if they feel kind of fuzzy, right, just go down to a simpler example. Pick a clock of, 1,000 hertz, right, or 4,000 hertz, and divide by 4, you get an instruction clock of, 1 kilohertz, and do some of these calculations from there. Let's see, so why do some instructions take 1 or 2 cycles? So conditional branches, for example, let's say you're executing some code. And so you execute this instruction, and then you do a branch if not 0. And you've got some other instructions, and over here you've got go. So suppose we don't take the branch. If we say branch if not 0 and the 0 bit is not set, this instruction does nothing. It changes nothing, it updates no bits, it doesn't modify any file registers. It's effectively a no-op, right? And a no-op, like most other instructions, takes a single cycle to execute. But if we end up taking the branch, if we find the Z bit is not set, then what we're going to do after this instruction is we're going to come down and we're going to execute this instruction. Well, there's a detail here. Remember, we have this pipeline. We fetch an instruction, we start executing that instruction while we fetch the next instruction. We execute that second instruction while we're fetching the third. So while we're executing this instruction, we're fetching this instruction. But if we end up taking a branch, guess what? That instruction that we fetched is not the next one we're going to execute. So now we come down here, we're supposed to execute this instruction. Well, the first thing we have to do is we have to fetch it. And then we have to execute it. It's that new fetch that takes an extra cycle now. We've broken our pipeline basically by breaking our continuous execution chain from one instruction to the next to the next. And the prefetch that we did to keep our pipeline full wasn't the right prefetch. So we flush the pipeline, right? It's sometimes called a pipeline stall. And pipeline stall, that's when your clock speed, your effective clock speed goes down. And so it takes 2 cycles for a branch. And remember, you know, most of these instructions actually take 2 instruction cycles to execute. The pipeline gives us the illusion that it only takes 1, but it actually takes, you know, if we say clear file register flag, it actually takes 2 instruction cycles to do that. But we started executing this instruction by doing the fetch. We started fetching this instruction while we were executing that one. So this is basically just breaking the pipeline, and we're just seeing the true time that it takes to execute most of these instructions, which is 2 cycles. And as I've mentioned, if you take a computer architecture class, you'll spend so much time just looking at pipelines and throughput depending on branches and keeping the pipeline full and so on. Let's see, it takes different cycles depending on if the condition is true or not. Yes, exactly. The instruction frequency always a fourth of the system clock speed, such as question 61. 61. Yeah. So on the PIC processor, it's always 1/4 of the system clock speed. But on other processors, it's different, right? On you know, x86, there's a bunch of clocks, but they're generally, you know, gotten by dividing a sort of fundamental system clock, and the division factors are usually soft. They're sitting in registers, and you can change them. And this is how you can overclock, you know, a CPU. You can say, okay, instead of dividing the system clock by 4, let's divide it by 3, right? And now your instruction clock runs a little faster, and so you can start getting into trouble like that. Are there any situations where the instruction frequency won't be a fourth of the system clock speed? Not for us. For us, it's always going to be a fourth, but definitely for different processors, different situations. And generally, the more complex the instruction set, probably the more system clock ticks you need to do an instruction, but that's an overarching generalization. All right, other questions?
Considering the code 66.
Mm-hmm.
As I was going through it, I realized that like clearF count makes it to 0, then if you decrement count, are we going into the negatives here, or is it just going to stay at 0?
It'll definitely decrement it. But is it negative or is it 255? It's purely a matter of interpretation. But if you start with 0, 0, 0, and you want to subtract 1, well, we can add negative 1. And if you want to know what negative 1 is in 2's complement, that's positive 1. Complement all the bits and add 1. That's negative 1. And that's a good one to recognize. You'll see F or FF or 8Fs pop up a lot. It's a quick view of negative 1. So if you take 0 and you add negative 1, you get negative 1, but you know that's also 255. If you look at this in the simulator, you know you'll see this if you look at it in binary. It's up to you whether you interpret that as negative 1 or 255, but it definitely decrements from 0 to something different, and in particular to this value. And then if you keep decrementing that, you know, you'll go down to this, and so on. And after 254 or more decrements, you'll end up back at 0.
Cool. That means I got it wrong, because I was like almost to the end of the homework, and I was like, wait a minute, hold up. My brain is so fried. I think it decrements into 0.
Okay. No biggie. And yeah, I think you'll also generate an underflow. I don't know if we have underflow on the status register. We have an overflow bit. And this one here would set the negative bit, so we could see that. Windows, go to the calculator app and tap programmer mode. It'll give you a nice bit shift calculator translate. Yeah, that's cool. So yeah, there's calculators out there that that do this. I have one on my phone. I think it's called RealCalc, that will switch between bases and so on and so forth. So that can be fun to play with. Definitely try to get good at it by hand also, and use some of those tools and apps to sort of help you in that process. But particularly if you're CS, you want to get really good with binary and hex, because it pops up a fair amount. All right, other questions? Go ahead and send me a here message as a direct message. Let me know that you're here. All right, and I've posted homework 6. Well, homework 6 was posted, you know, in the beginning of the universe, but homework 6 is open right now. It's due in a week, and my plan today and Thursday is to go through pretty much everything you need for homework 6. We'll definitely go through everything about timer 0, timer 1, timer 2, and hopefully get into CCP1 con, CCP1 RL. If we don't get to these last few questions, then I'll push those off to the next homework. But for now, my plan is to get through everything you need to do questions 71 through 103. So you should be fine on the homework. Now, these questions, there's not a lot of code to write in these, right? All of these questions are doing calculations on paper related to, you know, how long instructions take, how many instructions you do per second, things like that. They're all kind of, you know, pencil and paper kind of exercises. I really want you to show me your work is in addition to your final answer. If you just write down the answer, right, if you get it perfectly correct, okay, I'll give you credit for it. If there's anything wrong, it's a 0 unless I can follow your line of reasoning. So so definitely show your work on these, show me your thought process, right? And take the time to try to figure out how to do these instead of just trying to get the right answer, because you know, the goal of the homework is to help you nail down some of these concepts. So, and this is all we're going to do for the rest of today and for Thursday for the most part, is play around with timers. I lost my little countdown thing. There we go. All right. All right. Oh yeah. Let me. I graded your lab and posted that back with comments, and the labs look good. Traffic light. Okay, so now that's officially our last traffic light control circuit for the whole of Clark curriculum. So you're done with traffic lights. Yeah. So the labs look good. So most people got the code working. Most people did a really good job demonstrating the code. So when you demonstrate your code, right, you don't necessarily need to take the reader through, you know, every step of your assembly language code. You don't need to take a screenshot and say, you know, here I've set addcon 1 to 7f, right? You can assume that you know, at the point of this lab, the reader is versed in everything that came before this lab, right? So they know how to start up MPLab, put in code, set breakpoints, things like that. What you really want to demonstrate, for example, with the traffic light controller was, okay, so if there are no cars present, then let's say the western light is green. So set up your inputs using the stimulators, right? and step through your code, you know, get it to the point where it's back at the top of the loop, and just show the values of port A and port B. And, you know, you can do that with a few screenshots, and then you can sort of defer to like making a table maybe, and you know, say, you know, these bits show you that, you know, this one is a green on the western light and these are red on the east and south. And then a car shows up to the south, right? So hit your stimulus and step through your code until your light turns yellow. And now take a screenshot of your port A and port B, and, you know, comment that, you know, you can see there's a car to the south, and you can see that the western light is turned yellow, the other lights are red. And then run through your code till you get out of your delay loop and take another screenshot. And now you can see that the southern light is green and the other lights are red, right? So you're documenting your observations as you go through your test, hopefully following your test plan. Test plan is really nice if you sort of have, you know, something in your report that says test plan and then list what you're going to do, right? And a lot of people sort of integrated the test plan in with the observations and the procedure and a discussion and so on. But, you know, again, somebody's going to take your report, try to reproduce the results, right? So here's the test plan. I'm going to set my inputs to this, and then that, and then this, and I'm going to step the system and so on. So all those pieces were in there for the most part, which was great. People's code seemed to work well, which was great, and some good new experiments again. So keep that up. If you have questions about my comments on the lab, definitely ask. So flowcharts. Flowcharts are looking good. I made some comments about adjusting the level of detail up or down in a few cases, but in this current lab, we have interrupts, right? And interrupts don't really work with the flowcharts that we've been writing, because, you know, a flowchart, you go from one box, you follow the arrow to the next box, and so on. But when you get an interrupt, what happens? You jump somewhere else. So here's a way to do flowcharts for interrupts. Assuming you can spell interrupts. So, you know, here's our main program, and we do some init, and we do some other stuff, and maybe we do some stuff here, and, you know, we got some loop going like that. But when you get an interrupt, you know, presumably you've set this up so that when, say, a high priority interrupt occurs, something else happens. So you can represent that in your flow chart by, you know, putting something in here and saying something like, you know, int 0 and showing what to do. Or by saying, you know, high priority interrupt. If you have multiple high priority sources, you could put your oval with high priority interrupt, and then you could say, you know, is int 0 interrupt flag set? And if it is, then you go ahead and you do some stuff, and if it's not, then, you know, is the RB interrupt flag set? And so on. And at the end of this, instead of saying end, that's where you do your ret fee. So you return from interrupt. And then you could have another piece of your flow chart, like low priority interrupt, and go on from there. And you kind of need something like this, right? Because I can't put my high priority code in this part of my flow chart because I don't normally execute that code. It's interrupt driven, it's event driven, so it's kind of a separate thing that happens. And with interrupt driven code, these flowcharts will definitely help you, right? They'll help you really nail down kind of what you need to do here as kind of its own task, right? And then your main program is usually its own thing, and a lot of times our main program is really just, you know, it's just an infinite loop. It doesn't do anything, and it's just kind of hanging out waiting for events to occur. All right, so let's talk about timers. So, we know how to do interrupts. We've gotten more practice setting up special function registers, right? So those are the mechanics that we're going to use in working with the timing subsystem. So first of all, there's 4 timers on the PIC processor. They're called timers 0, 1, 2, and 3. And 3 of them are very similar to each other. Timers 0, 1, and 3 are very similar to each other. Timer 2 is a little bit different, but in a cool way. So we're mostly going to work with timer 0 first. Okay, we're just going to play with that. We're going to talk about timer 0 a lot. But then once we understand the mechanics of using that timer, it's pretty easy to use timer 1 and timer 3. And once we're versed in those, then we can talk about the peculiar aspects of timer 2. And if we're really comfortable with, you know, timer 0, then talking about timer 2 is just changing our understanding of one thing. But we don't want to try to tackle those all at once. So we're going to concentrate on timer 0 for a big part of today's class.
4 timers, right?
4 timers total. And if you go to the data sheet, they each get their own chapter, right? Timer 0, 1, 2, and 3, chapters 11 through 14. And they're pretty short, right? 4 or 5 pages each. By the time you get to timer 2, it's 2 pages long, right? So most of the emphasis is done on timer 0. And most of what we have to do in this is figuring out these special function registers and knowing how to set those up. All right, so here's the idea of a timer. Imagine that you're in a hotel and you want to do something in 2 hours. All right, maybe you're going to take a nap or read a book or play a game or something, but 2 hours from now you want to stop what you're doing and start doing something else, right? And so you want to set a timer that will let you know when 2 hours have passed. And, you know, if you got a phone, you just go ahead and you set the timer to 2 hours and you're done. But imagine that in the room, there's an alarm clock, right? And it's like an old-style mechanical alarm clock. So it's got hands, you know, that move around, and it's got a little red hand that you can turn to some, you know, point on the dial, and when the time gets to that point, your alarm starts to ring, right? So so you want to wake up in 2 hours. So what do you need to do to set this alarm to wake you up?
You need to have it when the timer is done to trigger an interrupt, right?
Okay, so you need to have something happen when the timer's done to wake you up, because if you're asleep, you're not going to be staring at the clock. So something like an interrupt. And let's see. See if I can find a picture. All right, so there's a good picture of an alarm clock. So maybe not a good picture. So this silver hand that's pointing at 9, right? That's the thing that tells you, you know, the alarm's going to go off at 9 o'clock. If you move that to 10, the alarm will go off at 10 o'clock, right? So how do we decide where to set that time at which the alarm should go off?
It might be like a special function register.
No, just with an alarm clock.
Oh.
We'll go to the pick later.
Just on that specific alarm clock.
Sure.
Normally there's a mechanism in the back that states what time. Like sometimes on those old ones, you would set it to that time. You'd click on setting it. There'd be like a set button, and then you'd like go back to normal time.
Okay. So So how do we know what time to set it to?
You would know from the little things up front by the windy things. Old ones like that, you would just wind to where you would need it, set it, and
Where do you need it? Where do you wind it to? It's a really, really kind of ridiculous question I'm asking, but I'm trying to break this down to a ridiculous level.
You would set it to the time that is visible on the front.
What time? 2 o'clock, 4 o'clock, 8:30?
Whatever time you want.
How do you know what time you want?
You would need to get the time and add 2 hours.
Ah, there we go. Okay. So if we want to wake up in 2 hours, we need to take the current time plus 2 hours, and we set the alarm to go off at that time.
So are we talking a one-time alarm?
Sure. I mean, it'll do it again the next day, but so if it's midnight, we would set the thing to say, okay, wake me up at 2 a.m. If it's 4 in the afternoon, we would set it to say, wake me up at 6 in the afternoon. If it's 1:30 in the morning, we'd say set it to wake me up at 3:30 in the morning. But we kind of need to know what the current time is and then add, some offset to that and say, okay, wake me up at that time.
I'm a little confused. Why are we basing it off of current time versus like a standardized origin time,
I think
like
it would-
at 0000?
I think it would have to be that the chip has a real-time clock, and you can't just, if you want to have something that is like a countdown timer for 2 hours, you need to get what the current time is and add 2 hours. You can't just base it off of like a static time, I don't think, right?
So I'm still thinking mechanical alarm clock here. I'm not thinking about the PIC processor yet. I'm just thinking of this general question. You're in a hotel room, there's an alarm clock, you want to wake up in 2 hours. In order to set the alarm, you got to know what the current time is. Add 2 to it, that's what you set the alarm to. Does that make sense?
Yeah, I just can't help myself. I have to think about the pig.
That's okay. You can't just set the alarm to 8.
Issues because I was raised military time, so I'm thinking like
That's fine.
it's kind of weird. I've never thought of just adding. It's just automatic.
Yeah, it's you can't just go into you can't just pick up a clock and set it for 0800, right? Unless if you want to wake up in 2 hours, well, that's great if it happens to be 6 in the morning right now. But if it's noon and you set the alarm for 0800, you're going to sleep until tomorrow morning, right? So you got to know what the current time is, add 2 to that, that's what you set the alarm for.
It would be an interesting feature if an alarm clock had some kind of button that when you press, it automatically goes to the alarm. What do you call it? Arm goes to the current hour and then
Yeah.
it goes to beyond it.
That would be cool. And most of us, we have a phone or something that we use to wake up, so this is a non-issue. You can set a timer and just say, wake me up in 2 hours. So maybe it's a bad example. But you need some way to say, when do you want the alarm to go off? Let's leave it at that. What else do you have to do? You have to turn the alarm on, right? Because whether it's a timer on your phone or it's an alarm clock on a table, right, there's usually some way to say turn it on or turn it off, right? So you need to be able to turn it on. You also need to be able to turn it off so that when it's ringing, you can stop it from ringing once it's gotten your attention. It's also got to do something when time is up, right? So some action when time is up. which is usually ringing a bell or making a sound or something like that, but it could be, you know, turning a light on over your head or pouring water on you or something, right? So there's something that happens when the alarm, when the time is up, that gets your attention. So that's like an interrupt. All right. So so on the PIC processor, let's look at timer 0, right? There's a register inside called timer 0L. There's also a timer 0H, but we'll just deal with L for now. So timer 0L, it's an 8-bit register. It's a special function register. And this is the thing that we can use to keep track of time to let us know when a certain amount of time has passed. So let me just go into some code. Let's see. All right, so we're just going to write some test code here. So I'll do my include, I'll do my origin statement. And I'm going to set up a couple of bits in this particular register, and we're not going to worry about what those mean quite yet. Let me just go ahead and set these up, and let's see what happens, and then we'll start talking about what these do. So I'm going to set up 2 bits. So I'm going to CS. So that's T0 con as in configuration. And what I want to do is I want to clear this bit, T0CS, and set this bit, timer 0, on. So I'm writing bit clear file register T0 con, that's the name of the register, comma T0CS, that's the name of the bit. Right? And we're not going to use magic numbers. We're not going to put 5 in here, right? Because this is the 5th bit. We're going to call it T0CS. And then I want to set this bit, timer 0 on, to be 1. Well, it's got a default value of 1, so we're okay with that. All right, so let's Alright, pretty simple program. Oh, let me go ahead and set up addcon1, because I've told you to always do that, even though we don't need it. We'll keep good habits. Alright, now I'm going to put a breakpoint right here. I'm going to build this. I'm going to run it. I'm going to pause it. Alright, so this code, you know, it just sits here and it loops forever. Oh. Hold on. I gotta do that weird thing that I have to do, but you don't. So I gotta tell it to do absolute. Build absolute mode. Okay. I'll build that. I'll run it. I don't get errors this time. So I'll sit here and it's just kind of hanging out here. All right, so let me add a variable. So I'm going to add timer 0L. And timer 0L right now has a decimal value of 25. As I step through my code, you can see my timer 0 value keeps changing. It keeps incrementing. It's incrementing by 2. Right? Even though all I'm doing here is just a branch to myself, I'm just sitting here spinning, but it looks like as my code is executing, this register keeps going up in value. It's decimal 73, 75, 77, 79, and so on. And that will keep happening. If I set it to 250, right, it increments 252, 254, and then when I increment it again, it's going to go back to 0. So it rolls over as you're incrementing as well as decrementing. And this just keeps counting by 2 every time that I execute an instruction. Now if I make this a little more interesting and I throw in a no-op here, let's throw in a pair of no-ops. And let's rebuild that and run it. So right now I'm looking at my timer register right down here. So my timer register is 1. And then it increments to 2. And it increments to 3. And then it jumps to 5, 6, 7. And it jumps to 9, 10, 11. And it jumps to 13. So what's going on here? Why is it jumping by 1 or 2?
Number of cycles.
Number of instruction cycles. Right? And this is this thing where branch instructions take 2 cycles, whereas most instructions take 1. So it looks like every time that an instruction cycle happens, timer 0L gets incremented by 1. If it's an instruction that takes 1 cycle, it goes up by 1. If it's a branch that takes 2 cycles, after I execute this instruction, timer 0L will increment from 15 to 17. So timer 0L is tracking how many instruction cycles have occurred. And we can write this register. I can load a value of 200 in there. And now it'll go up to 201, 202, and then jump to 204, and so on. All right, so that's the first thing to keep in mind, right? Timer 0L will count the number of instruction cycles that have occurred. But this only happens if I clear this bit T0CS, timer 0, clock source select. If I make that a 0, it says use the internal instruction clock cycle as the source of, what we're counting. Now if this is a 1, it ignores the instruction clock ticks, and I need to use a signal on a pin, T0CKI, and every time I pulse that pin, then timer 0L would count. So by clearing this bit, T0CS, we basically take timer 0 and we have this register count how many instruction cycles have occurred. Alright, so that's the first thing. And if questions come up along the way, definitely let me know. Let's take a look at the intcon register. So intcon is 8 bits, and I want to look at that. So intcon is got a value of 1 right now, right? I think we can clear it. Let's see. That's interesting. All right. Well, let's just see if this works. So I'm going to keep stepping my code. So it's at 252, and we're going to watch the intcon register and see what happens to it. So right now it's got 0011 and then 4 zeros. And timer 0L is 252, now it's 253. It's 254. Remember, we're going to take 2 more cycles to do the branch. It's going to go up to 256, which will roll over to a 0. But when that happens, look what happened. Our intcon register changed value. In particular, this bit right here changed to a 1. So the third bit of intcon just got turned on. And the third bit of the intcon register is something called timer 0IF. That's the interrupt request flag. So we got 2 things happening now. Every instruction cycle, timer 0L increments by 1. And it looks like when it overflows, timer 0IF gets set to a 1. In other words, timer 0 requests an interrupt. Now we don't have interrupts enabled. We don't have timer 0 interrupt enabled. We don't have global interrupts enabled. So the interrupt's not happening. But when timer 0L overflows, this interrupt flag gets set. And remember, these flags stay set until you clear them. So that third bit is still a 1. I can clear this out. And now as I tick through, right, timer 0L is incrementing. This third bit is still a 0. And if we jump timer 0 ahead to a value where it's close to overflowing, once it overflows back to 1 in this case, that third bit of intcon gets set. So we've got enough now to set up a way to wake us up after a certain number of instruction cycles. If we clear this flag, so put a 0 back into intcon, and if I enabled interrupts from timer 0 and I enabled global interrupts at the right priority, right now timer 0L is a 1. After 255 instruction cycles, it's going to overflow. It's going to request an interrupt. And we can translate instruction cycles into time, and we can translate time into instruction cycles. Right? That was the last part of that previous homework set. So if you know what your system clock frequency is, you know how long an instruction takes. So if we wanted to set an alarm to wake us up in half a second, all we have to do is say how many instruction cycles does that correspond to, and then set things up so that after that many instruction cycles, this timer 0L will overflow. All right, so this is the next challenge in using the timing subsystem. So suppose we want an interrupt in 100 instruction cycles. All right, we want, for whatever reason, we want to be interrupted in 100 instruction cycles. We don't care what those instructions are doing, but after 100 instruction cycles have passed, we want to generate an interrupt, jump to location 8, for example, and do something. Toggle an LED or something like that. And we know that we know 2 things. Timer 0 increments every instruction cycle, and when it gets to 256, we'll get an interrupt. So using those 2 things, what can we do to set things up so we'll get interrupted 100 instruction cycles from now? This is sort of the heart of the whole subject.
If we were using the same loop, we would just need one branch loop and to set the timer to 155 decimal initially.
Okay, why 155?
Sorry, 156.
Okay, why 156?
Because that plus 100 would cause the overflow.
All right. Everybody catch that? Set timer 0.
Please?
Set timer 0L to 156. If we do that, then after 100 instruction cycles, this will have incremented to 256, which will overflow, which will generate timer 0 interrupt request. And if we enable interrupts, that's it, we're done. It'll generate an interrupt after 100 instruction cycles. So if we want an interrupt after 200 instruction cycles, set timer 0L to 56. Because of two things. One, every instruction cycle this will increment, which means after 200 instruction cycles this will increment to 256, which will overflow. And two, when this overflows, it generates an interrupt. All right, questions about this? This is the whole heart of the subject, right? Incrementing a register, setting it to a value so that after a certain number of increments it overflows. That's pretty much all we're going to be doing. So if I do something like this, move decimal 246 into timer 0L, and then go into this loop, well, if I go ahead and build this, and run it, and start stepping it. So here we're loading our magic value into timer 0L. And if let me do this a little differently. So we don't have to deal with branch instructions. Alright, so we're going to move this magic value into timer 0L. And now we're going to go, and I want you to watch this intcon register and see when it turns red. So we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 instructions, and we got our interrupt flag. So I wanted it to happen after 10. It happened after 12. That might have been a glitch in my piloting. Alright, so let's go 1, 2, 7, 8, 9, 10, 11, 12. Alright, so it takes a couple of instructions to get things going in the beginning. But that's basically how we set this up, right? Now we still need to, you know, turn on an interrupt subsystem so that when this interrupt flag goes high, this timer 0IF, that'll actually take our code to somewhere else, like location 8 or 18. But that's just interrupt stuff, which we've done. For some reason, Zoom has disabled me plugging in USB devices. Well, that's annoying. I do find that exiting Zoom and restarting it sometimes helps with things like that, because sometimes it refuses to use my soundbar. But we'll be here if you want to hop out and hop back in. All right, so questions about this? All right, let's go ahead and wire in interrupts just for kicks. So so we're going to turn on timer 0 interrupt enable, and we're going to enable high and low priority interrupts, and I'm going to set priority levels. So let's do our usual interrupt setup. So we'll go in the Archon, we'll set up IPEN. And we'll go in the IntCon register and we'll set timer 0 interrupt enable. And timer 0, is it always a high priority interrupt? Timer 0 interrupt is generated when the timer register overflows. Timer interrupt flag. Timer 0 interrupt cannot be in processor low. Let me take a peek at priorities. Alright, so timer 0, we can also set the priority with timer 0 IP. The default value is 1. Timer 0 IP 1 says it's a high priority. So we're going to leave that as is. So I'm going to set up global interrupt enable high and global interrupt enable low. That should arm our interrupts. We'll go ahead and we'll load a value into timer 0L. We'll turn on the use the instruction clock, and then we'll just go into a loop that just hangs out. Alright, so my code starts at location 0. First thing it does is branch to my label start. And my start code is at location 20, so it's out of the way of the interrupt code. And then let's put some interrupt code down here. And I don't know, what should we do in here? We'll just do a couple of no-ops, and then we'll, remember we have to clear the interrupt flag after an interrupt occurs. So we're going to clear timer 0 IF in IntCon. and then we're going to ret phi. All right, this makes sense. So our goal is going to be to set things up so that once we get to our loop, after 10 instruction cycles, we'll suddenly jump down to this interrupt code.
We could also like cascade the timer like with the delay count in lab 3, right? So we could take even, so if it takes 255 cycles, we could multiply that by 10 if we increment or decrement a delay count so that the delay will execute 10, 15, however many number of times, right?
Well, this will always increment every instruction right now. But we could, you know, set something up in our interrupt code so that it has to interrupt 10 times before something happens. And we could effectively extend it like that. But we'll see other ways to extend the time in a moment.
Okay.
Alright, so let's go ahead and run this. And so I'm going to come into my loop, and I'm going to execute this, and this is going to take about 3 instruction cycles per iteration of the loop. So I'll come in here and I'll keep executing, and then all of a sudden I'm down here in my interrupt code. Alright, did everybody catch that? This is magic. Let's run it once more. We'll go ahead, we'll set up the timer, we'll hang out in our loop. We loop a couple of times, 3 times, 4 times, and all of a sudden we're down in our interrupt code. And this is pure magic, right? This loop clearly says do nothing, go back, do nothing, go back, do nothing. That's all we should ever be doing, but we've arranged it so that after a certain number of iterations, now we're down here at location 8. And what we could do down here, for example, is, you know, toggle a flip-flop, or add 1 to our thing that's keeping track of system time, or, you know, whatever it is we want to do.
So the entirety of our code is based on if there was an interrupt of some kind.
Mm-hmm.
Okay.
Now if I initialize this to 236 instead of 256, well, it kind of works the same, except we come in our loop and we spend more time in our loop, but eventually the timer expires and we jump down to our interrupt code.
So it's basically just like event-driven, asynchronous like JavaScript or something.
Exactly, yeah. All right. Is this going to happen again, though? We're going to go through... Yeah, this is how basic electronic clocks operate. And you can build a nice little digital clock out of a PIC processor without too much work. I have one sitting in my office, but it's, you know, quarantined. But it's not a very complex circuit.
That's literally a project I wanted to try after this class.
Cool. Well, you can do it.
Clock out of it.
Yeah.
Like, a binary coded to decimal clock.
Excellent. Yeah, the PIC processor is totally capable of doing that. And it's not all that much hardware to wire it up.
You can also use the built-in timer to make the speaker and play Yankee Doodle at the same time.
Yes, totally. Yeah, so you can do this for tone generation, right? If you want to generate a A440, you need to basically toggle a value going to a speaker, you know, 440 times a second. So you figure out how much time that is, you translate that to instruction cycles, and then you set up your timer to interrupt after that many instruction cycles. Alright, so here's a bit of a sad thing, right? We go back to our code and we're back in our loop. Remember, this is supposed to interrupt after 20 instruction cycles, which is about 7 times through the loop. Well, it's not interrupting anymore. Why not?
Is that because we started a higher decimal at the very beginning?
Yeah, so when we overflowed, or overflew, our timer 0L went back to 0, and it's still counting up, but it's counting up from 0. There's 140, there's 150. It's going to take a lot longer before it overflows, because after the overflow it went back to 0, whereas the first time through we initialized it to 236. Alright, so now it's back to 236, and after several iterations of our loop, bingo, we're back in our interrupt code. So if we wanted this to interrupt every 20 instruction cycles, not just once but repeatedly, what should we do?
Maybe right after the interrupt code and before the rectify, we make it so that our decimal was back at that specific
Awesome.
number.
I love it.
So if we wanted to, we could potentially just set a watchdog timer, because this also has a watchdog timer, right? And then we could save some space on code.
Well, the watchdog timer is really particular. I think it's a fixed amount of time. Maybe there's a little bit of variability in it, and when it expires, it resets the processor. So it's a pretty hardcore response. And this is much more controllable. But we could make our own version of a watchdog timer with this. That would definitely work.
So is that one of the 4 timers, and why you only really mentioned 3?
No, the watchdog is totally separate. It's a completely different system. But there's 4 fully customizable timers like timer 0.
Alright.
Cool concept. Alright, so let's run this. We'll go through our loop several times. Bingo, we're in our interrupt code. We're going to go through our interrupt code, come back in here, go through our loop a few times. Back in our interrupt code. Now, we're only going through our loop about 5 times before we get interrupted, whereas when we first ran this, it took several times through. 4, 5, 6, 7, 8. Right? So what's going on in here is that once we get our interrupt, we reset timer 0. While we're in our interrupt code, timer 0 is still incrementing. There's the 236 that we just loaded in. We do a no-op in our interrupt code. Now it's 237. It takes a couple of cycles to start incrementing after you load a value. We do the ret fee. It's up to 239 already. Right? So it's constantly incrementing timer 0L no matter where we are in our code. It doesn't understand that we're not back in our loop here where we wanted to, start incrementing. It's anytime the instruction clock ticks, timer 0L gets incremented.
So this is what you meant by we have to actually do the math.
Yeah.
Because we're going to have to be able to tell if we want a specific amount of increments.
Right, and that's exactly the next part of this, is if, usually we want to interrupt after a certain amount of time. So if we know that it takes, for example, 125 microseconds per instruction, and let's say we want to interrupt every, I don't know, 4,000 microseconds, so 4 milliseconds. Well, we have to translate that into instruction cycles. So if it's 125 microseconds per instruction, 4,000 microseconds would be 4,000 divided by 125, which will be, I think, 32 instructions. With a question mark for my math. Right? So then if we know we want 4,000 microseconds and we know that's 32 instructions, so we would initialize timer 0L to 256 minus 32 would be 224. But if our system clock was faster, if it was 1 microsecond per instruction, then we would need to load a different value in because we would want a different number of instruction cycles. So all those questions at the end of the previous homework where you're calculating instructions and time and so on and so forth, those are all coming into play here.
What's the default timing again?
So on the PIC processor, if you don't do anything else, it's about 32,000 instructions, 32,000 system clock ticks, so about 8,000 instructions per second. Which is our 125 microseconds per instruction.
We're pretty much just going to operate at that no matter what, of course, right?
Not necessarily. So you know, some questions will say assume a 1 megahertz instruction clock, and it makes your calculations easier. And since we don't have a physical chip, it's a little immaterial. Although if you watched my video on that graphical tool that I've offered for you to use, that is assuming a system clock around 32 kilohertz. So depending on how fast your CPU is, you can get something close to real time with that. In other words, if you set up that delay loop that was built around a 32K clock that does a tenth of a second, if you use that in that tool, it actually comes out to pretty close to a tenth of a second, at least on my CPU. Faster or slower CPU, it'll change. And that's a fun tool to play with when you're doing interrupts and timers, by the way.
In real life, when you're using the actual chips, if you do the calculations right, it's pretty much dead on, though, right?
Pretty much not.
Oh.
So there's a chapter in the text on the clocks and oscillators inside the system. Let's take a look at this actually, because it's interesting. So here's the best picture, I think. So this is the clock diagram. There's an internal oscillator, and it says int RC. So if you're electrical engineering track and you've done any of Izad's 200 level courses, 204, 52, you know about RC circuits, right? By taking a resistor and a capacitor, you can build a circuit that oscillates. And there's a circuit inside here that oscillates around 31 kilohertz. But it's built with a resistor and a capacitor. Well, that's not very accurate, right? If you heat it up or cool it down, the frequency will change, and it's pretty severe. But there's also an internal 8 megahertz oscillator, and I don't know how solid that one is. And then we have a multiplexer, Engineering 250 flashback, so we have 8 inputs. We can pick one of these to send the output based on 3 select lines, which come from this register called OSCON, oscillator configuration. And we can take either the 8 megahertz clock, or we can divide it by 2, 4, 8, 16, 32, or 64, get down to 125 kilohertz, or we can take this RC source, which is 31 kilohertz, and use that. Default value for OSCON, these bits, is 0, so the 31K source comes through. And that gets sent into another multiplexer, and these 2 bits of the oscillator control register can be used to choose either that internal oscillator or an oscillator coming in from outside. So you can hook an external crystal up to this chip and get very accurate timing, or you can use the internal 31K source and get very inaccurate timing, or there's options in between.
Interesting.
And a lot of fun to play with.
About, changing precision, and I guess this answers that.
Okay, yeah. This is also how you overclock, by the way. If you want to overclock the PIC, you can just pump in a really high-speed clock on these oscillator pins and set your configuration to use that.
You could probably get away with something really high, because I don't imagine it's a very fine manufacturing process.
Well, you know, I've challenged my students in the past to like do an experiment where they overclock the PIC and see how high they can drive it. Nobody's ever taken me up on it, and it's not much fun in simulation. But you know, when we're back in the physical lab, it would be a fun experiment to do. Just have it, you know.
I'll take you up on that one if I ever get one.
Cool, yeah. Have it do something, you know, like blink an LED and then see how much you can overclock it before it smokes. That would be pretty cool. All right, so we are past the worst of this at this point, right? We've got the basic mechanics down, which is load a value into timer 0L, and then assuming that we've said use the instruction clock cycle, every time the system ticks the instruction clock, this register gets incremented. And when it overflows, we get an interrupt request, and if we've enabled interrupts, then, you know, an interrupt is thrown. So here's a question. Using this approach, what's the longest interval we can expect to request before an interrupt occurs? And let's
55?
255 instruction cycles. Actually 256, but you know, give or take. If we initialize this to 0, then it's going to take a really long time before it overflows. So we've initialized it to 0. I changed the wrong spot. Let me do this. Alright, we initialize the timer to 0. You can see it's a 0 right here. It's going to start incrementing. It's going to take 256 instruction cycles before it overflows. With this setup as we have it right now, that's the longest possible interval we can have. 256 instruction cycles divided by 8,000, it's a fraction of a second. So what if we wanted a longer period of time? What if we wanted to wait for a whole second, or 60 seconds, or, you know, 30 minutes? We can't do it with what we've discussed so far, because the smallest value we can initialize timer 0 to is 0, and that takes the most number of increments, which is 256. So there's other mechanisms in here that will let us extend the length of time. And the first one we want to talk about is the prescaler. And so everything I've told you so far is mostly true. Every time that the instruction cycle ticks, timer 0L increments. Increments, increments, increments. Branches take 2 instruction cycles, increments by 2. No op takes 1, increments by 1. But that gets us to the overflow point really quickly. So what we can do is we can change that behavior and say, you know what? Increment me every other instruction cycle. Or increment this register every 4th instruction cycle. Or every 128th instruction cycle. And by making that request, it will take more instruction cycles to increment, and therefore it will take more instruction cycles before we get an overflow. So there's another register bit, another set of register bits in T0con which relate to the prescaler. So PSA says, do we want to use a prescaler or not? The default value is 1. And that value of 1 says there's no prescaler. But if we set this bit PSA to be a 0, then we're going to have a prescaler, and the prescaler is determined by these 3 bits. And if we set those bits to 0, we have a 1 to 2 prescaler. If we set them to 1, we have a 1 to 256 prescale. So let's play with this. Let's set up a 1 to 8 prescaler. And so let me make a picture and I'll show you. So these are T0 prescaler 0, T0 prescaler 1, T0 prescaler 2, and prescaler. All right, so I'm going to set the PSA bit to be a 1, sorry, to be a 0, to say I'm using a prescaler. And I want a 1 to 8 And a 1 to 8 says I should set these 3 bits to 0, 1, 0. Alright, so I'm going to modify my code. I'm going to set up T0con to say, hey, let's clear these 3 bits and let's set that bit. And when I do that, I should have a 1 to 8 prescaler. Yeah, everything is like powers of 2, which is really cool. You know what freaks me out, though? Like, the English system is all powers of 2 also. Like, you do, like, you know, a gallon, and a quarter of that is a quart, and a quarter of that is a cup, and an eighth of that is an ounce, and it's all power of 2 based, right? And the metric system, which is, like, modern and scientific, is, like, base 10, which is, like, human number of fingers, you know? So that seems backwards somehow. Alright, so let's set up a prescaler. Set up a 1 to 8 prescaler. So I'm going to say bit clear f T0 con, comma, T0 prescaler 0. And I'm going to set bit 1. I'm going to clear bit 2, and then I'm going to clear PSA. So that should set up a 1 to 8 prescaler, right? And we're just putting in those bit values and we're toggling them indirectly. Now you could just load this bit pattern in for T0 con, right? And move that into a literal and then copy that over. But then you've got a magic number, you know, a magic bit pattern. And if you're looking at your code trying to figure out what's wrong, you know, you got to go back to your data sheet and so on. So here, you know, I'm clearing those 2, setting that one, clearing PSA to say let's assign a prescaler, and we'll go from there. So let's build this, and let's go ahead and run it. And we're going to be watching this timer 0L register. Alright, so I'm setting up a prescaler. I'm going into my loop. Okay, timer 0L is a 0. I'm stepping through my loop, just jumped to a 1. I'm stepping through my loop, it jumped to a 2. Jumped to a 3. So it's every 2 or 3 iterations of my loop, timer 0L is incrementing. Right? Well, an iteration of a loop is 3 instruction cycles. So it's taking, you know, 2 to 3 iterations, that's 8 instruction cycles before this increments. So I'm going through a lot more of my loop before timer 0L increments. And those instruction cycles correspond to time. Does everybody see that? So in order for this timer to overflow, it's going to take 256 times 8 is 2048 instruction cycles.
Could you show the manual page on the scaler again?
Yeah.
Tiny bit confused.
So you turn this bit on to say you want to use a scalar at all.
It's 3 bits.
And those 3 bits specify a value, yeah, in tandem. So we went with 0, 1, 0, which made it a 1 to 8 scalar. If we set this to a 0, 1, 1, that would be a 1 to 16. So let's change this least significant bit to be a 1. So this will be a 1 to 16 prescaler. Come down in here in our loop and we'll wait for timer 0L to turn red. And it's about 5 iterations through the loop now before timer 0 increments. So with a 1 to 8, right, it increments after 256 increments of the register, and each increment happens after 8 instruction cycles, that's 2048 instruction cycles. And so that's approximately a quarter of a second. So if we wanted a 1 second delay, (256 times 32) is 8192. So if we set the prescaler to be 32 and we initialize timer 0L to be 0, then after, 8100 instruction cycles, we would get an interrupt. That would be about 1 second. Yes, you can change the scaler mid-execution, and it doesn't do anything particularly weird. It's really just kind of, there's a circuit that's receiving instruction cycle ticks and counting up to whatever the prescaler value is. So if you have a prescaler of 8, it basically counts up to 8, and when it gets past that, it resets to 0, and it says increment timer 0L. Now, if you suddenly change the prescaler to, 16 while it's counting, then it would, the next time it would have to get up to 16 before it increments timer 0L. And then if you change it down to 2, then if it was already bigger than 2, I think it would immediately increment timer 0L, go back to 0, and start counting from there. So I don't think it does anything too bizarre. And so you can start to make some sense out of these diagrams. So here's F osc, that's the main system oscillator, the system clock, gets divided by 4. That generates ticks in here. And that tick either increments timer 0L, or it goes through a prescaler, which basically forces a certain number of these ticks to occur before a pulse is generated to increment timer 0L. And then when timer 0L overflows, that generates the timer 0 interrupt flag. And here's that 2-cycle delay mentioned that we've seen. All right, so we got a bunch of things going on now. We've got T0con, which lets us, say, use the instruction cycle clock. It lets us turn the timer on and off. That's that 8th bit that we haven't really played with yet. It lets us set up a prescaler to say, hey, don't increment timer 0L every instruction cycle, increment it every other, or every 4th, or every 32nd instruction cycle, so that we can extend the time it takes to overflow. And when it overflows, it'll request an interrupt. It sets the IF flag. And then if we've enabled interrupts in the right way, that IF flag will generate an interrupt, and it can be high priority or low priority, and we'll find ourselves jumping down to, some kind of interrupt code. And then in that interrupt code, if we want another interrupt to occur after a certain time period, it's our responsibility to make sure that that timer 0L register is set correctly. Because when it overflows, it goes back to 0, and if we wanted it to count, just 10 instruction cycles, we would need to set it back to 246, for example. Although here we're setting it to interrupt after 10 increments, but we've got a 16 prescaler, which means it's going to take 16 instruction cycles to increment this once. And this has to increment 10 times to overflow, so it's going to be 160 instruction cycles before we get an interrupt. And so there are multiple ways to get the timing interval you want. Right? If I wanted to wait 160 instruction cycles, I could use a prescaler of 1 to 1, and I could set this to 256 minus 160. I could use a prescaler of 1 to 2 and set this to 256 minus, I forget what I was setting up. but you know, the same thing divided by 2, and so on. All right, so we got one more wrinkle here. So what's the longest amount of time that we could generate an interrupt request using the timer as we understand it right now? What would we set up to make the longest possible delay, and then we'll figure out what that translates to. So longest delay till interrupt. What should we set our prescaler to? $256. Got it in chat. All right, and what should we initialize timer 0L to? Initialize it to 0. Good. All right. So what does this translate to? If timer 0L is initialized to 0, it's going to take 256 increment instructions before this overflows and generates an interrupt. And if the prescaler is 256, it's going to take 256 instruction cycles before we increment this once. So this is going to be 65,000 instruction cycles. So under our default setting, 32 kilohertz, how long does it take to execute 65,000 instruction cycles? Ballpark number. How many instructions run per second? Yeah, about 8 seconds. So it's 8,000 instructions per second. So 64,000 instructions would be about 8 seconds. So it's a little more than 8 seconds. So set your prescaler to 256, set your timer 0L to 0, and after about 8 seconds, you'll get an interrupt request. Which is pretty cool, but there's two things. One, you might want something longer than 8 seconds. Maybe you want an interrupt every minute. And two, this is assuming your system clock is a pokey 31 or 32 kilohertz. If your system clock was running at 8 megahertz, right, this would take, you know, much less than 1 second to generate an interrupt. So we need a way to make the timing intervals even longer. And the way we do that is by using 16-bit mode. And so in our configuration register, there's this T08 bit. It's initialized to 1, which means to configure the timer as an 8-bit counter. But we can set that to 0 and configure this as a 16-bit counter. All right, so let me get rid of the prescaler stuff. And let me add another register down here, which is timer 0H. And let's build this and run it. Alright, so timer 0L is 246, and we're just going to keep incrementing this. 250, 251, 253, 254, and then it rolls back over to 0, and you can see we got an interrupt request. Timer 0H was 0 to begin with, it's still 0. We'll go into our interrupt code, we'll set timer 0L back to 246. We'll step through, we'll increment, it's up to 255, we'll execute one more instruction, it rolls over to 2, and timer 0H is still 0. the whole timing system right now is based on an 8-bit timer register. But we can say, you know, do everything that we've been doing, but let's treat our timer register as being 16 bits. And in that case, we have, as usual, a pair of special function registers, timer 0L, timer 0H, which collectively form a 16-bit register. And this 16-bit register overflows when it gets up to 65,535 plus one more. So how do we do this? We turn on the T0 8-bit register in T0con. So let's go ahead and do that. So we need to set that bit to a 0, so bit clear file register. T0con, T0 8-bit. Alright, so we clear that bit to make it a 16-bit timer. And let's build that. And let's run it. And let's start stepping through. Alright, so timer 0L is 246 right now. I'll zoom in. And let's start stepping this. So we're going to increment it. It's 246, it's 247, it's 248, it's 250, 51, 53, 254. The branch will add 2 more to it. What happens now? It goes back to 0. Ooh, that's not what I wanted to have happen. But it did not generate an interrupt. Alright, this timer 0H is a bit of a red herring, but let's bring this back up. Set timer 0L to 250. Right, and it looks like when timer 0L interrupts, when it overflows, it doesn't generate an interrupt anymore. Right, now if I set time, I don't know if I can do this on the simulator. Alright, let's try this. This may not work, and I'll tell you why in a minute. But timer 0L is 250, timer 0H is 255. There's 252, 53, there's 255, one more instruction. Our 16-bit register should overflow. Yeah, so that's a red herring. Alright, so ignore that weirdness. But take my word for it. If you load a 16-bit value into here, right, every time that the instruction cycle and prescalar generate a tick, this 16-bit register gets incremented. And when the 16-bit value overflows, then you'll get an interrupt request. Alright, but there's a bit of weirdness in here, which is in trying to look at timer 0 high or set it with the simulator front end, does not work the way you would expect. And this is just something quirky that we usually don't have to worry about too much. But let me do this. Let me preset my timer 0 high register to 255 and timer 0 low to 246. Alright, so I'm inside my loop. Timer 0 high is 255, timer 0 low is 246. We're going to step through a few instructions. Timer 0 L is incrementing. You can see it in red. It's 253. 254, the branch will take it up to 256. And then we jump down to our interrupt code. What's goofy is that when you look at timer 0h here in the variable, timer 0h is actually 0 now, but it's not showing you that. And we'll talk about why in a second. But that's the basic setup, right? So treat this as a 16-bit register, low 8 bits, high 8 bits, and this will only generate an interrupt request when the 16-bit value overflows. So now we can have a 256 prescalar times 65,536, which is the value this has to count up to overflow. Which will be, I think, 16 meg. So 16 million instruction cycle ticks. And if we divide by 8,000 instruction ticks per second, this would come out to 2,000 seconds. And so it's about, 40 minutes or so, 35 minutes, something like that. So a little north of a half an hour. Which isn't bad. So that's our range of options for modulating the time till an interrupt occurs. The initial value we load into the timer register, the prescaler, and whether the timer register is 8 bits or 16 bits. In addition to the speed of the system clock, which we don't usually get to pick in our code, that's usually fixed, but that affects the time ultimately. Alright, let's talk about the weirdness with timer 0h. And like I say, this usually doesn't pop up in our code, except for initialization sometimes. So there's two registers, timer 0 L and timer 0h. And together they make a 16-bit register. So there's a rule you need to use, and I don't think I want to go into the why of this rule right now, but I can later if you're interested. But, if you're doing 16-bit operations, so if you're in 16-bit mode, typically you need to, load a value into both of these. Okay, so here's the rule. You have to write the high piece first. And when you want to read the value, you need to read this first. So in other words, in my code, in my initialization, I wanted to set timer high and timer low. It's really important that I set timer high first. I'm going to go without a safety net here, see if I can break this. If I were to do the opposite, if I were to set timer low first, right, so I set timer low, I set timer high. Right, but I don't get my interrupt anymore. Alright, you want to see that again? So all I did was change around the order of these two instructions. And when I look in my simulator, timer low is 246, timer high is 255. So when I step through and timer 0L overflows, which it will do on the next instruction, my timer register should overflow, I should get an interrupt. But I don't. All right, so this will drive you absolutely batty if you get tripped up by it, but it's really easy to avoid. Just make sure when you're trying to set values for both timer low and timer high make sure you write into timer high first. And if you have code that's trying to read timer low and high, make sure you read timer low first. Okay, there's a really good reason for it. And if you want, look at figure 11-2. It has to do with this business over here. And in a nutshell, timer 0 high is not actually the high part of this 16-bit register. It's a temporary register that's used to transfer values to and from this upper part of the 16-bit register. But that happens in response to things that you do with the low part. I'm definitely not going to go into details right now because that's like a really long, complex discussion, and it's better in the beginning of class than after 2 hours of lecture on timers. But just make sure you do that, right? When you're setting a value into the 16-bit register, write the high piece first, and then write the low piece. And then you have great happiness. So write the high piece first. Go ahead and run through, interrupt. There you go. All right, I think that is all that we need to do for timer 0. And that lets you do the bulk of the homework questions in the first 2 sections that talk about timer 0. And then this is stuff you're going to use in lab 5. So what do we have to do? We have to, well, you have to think about this, and then we need to, on Thursday, talk about timer 1. And timer 1 is almost the same. It has a prescaler, but not as many prescalers. It can be, you know, 1 to 2, 1 to 4, 1 to 8, 16 or 8-bit operation, different configuration register, different bit values, and so on, but, you know, more or less the same. And then timer 3, I don't even know if they talk about timer 3 in here. I'm on my cheat sheet. High byte, low byte, little nibble, itty bit. Excellent. And then timer 3 is basically the same. And then timer 2 we'll talk about separately. And timer 2 flips some of this stuff on its head. So I don't want to talk about it. I'm going to say don't look at it until you feel more comfortable with how timer 0 works. But just keep this in mind, right? Timer 0 register gets incremented periodically. When it overflows, it generates an interrupt. The number of times it has to increment depends on its initial value. What time are you starting from, right? If it's starting at 0, it takes 256 increments. If you're starting at 200, it only takes 56 increments. This was what I was trying to lead to with the alarm clock thing in the beginning, but forget that. But you know, its initial value tells you how long it takes till it overflows. And the overflow point depends on whether it's an 8-bit register or a 16-bit register. 8-bit overflows at 256, 16-bit overflows at 65K. And how often it increments depends on the prescaler. 1 to 1 increments every instruction cycle. 1 to 2 increments every other instruction cycle. 1 to 256 only increments after 256 instruction cycles. So bigger prescaler, less often increments, takes a longer time to increment, takes a longer time to overflow. 16-bit takes a much longer time to overflow because the overflow value is bigger. And if you start with a smaller value in the timer register, it takes more increments to overflow, so that makes a longer period also. Shortest interval that you could set up would be nominally 1 instruction cycle. Right? Prescaler of 1, 8-bit register, initializes at 255. Basically, after 1 instruction cycle, it's going to overflow, generate an interrupt. That's a really kind of weird thing to do. It's like setting an alarm for every 1 second. Right? You're not going to get anything done because you're going to spend all your time turning off the alarm, you know, or snoozing it. All right. That's a ton of stuff to digest. Hopefully the order in which I presented it is such that it kind of builds up in complexity and I think the earlier stuff is the most foundational, right? The basic mechanics of the timing, and if you can understand those, right, nail those down before you worry about the prescaler, before you worry about 16-bit mode and so on. And the simulator works pretty well with this while you're stepping it and looking at instruction counts. I don't think these translate to real time very well, but you can play around with that, right? Set up a big long delay, put a interrupt breakpoint, and just let it free run and see how long it takes to get there. All right, any final questions? All right, I will switch to my office hours. Shoot me a final attendance note. Let me know you're still here. And I will see you in office hours, or I will see you Thursday. And have a good one. Thank you.
Thank you.
Have a great day. Thank you.
You too.